Okay, I guess you might think that PD is not too bad if you can solve one, right? So we'll solve a PDE. Okay, it's called the wave equation. I'll explain the meaning of this when we get to the heat equation, and if you compare the two, there's a very easy way to understand that mathematically or physically. But let's just say that this is a differential equation, partial differential equation that's given to us, where C is some constant. Okay? Moreover, we're going to say that X is all reals, and time t is positive. We don't go backwards in time, we only go forwards in time. Okay? And we're going to add in the initial conditions. So see, u is a function of x and t, and the initial condition is what happens at time t equals to 0. So at time t equal to 0, the initial shape of the wave is given as f of x. Okay. But then, because this is a second order differential equation with respect to t, you have to provide two initial conditions. So I'm going to give you the value of ut x0. And if you differentiate something by time, that's the velocity, right? So this will be the velocity of the wave. So I guess here's what's happening. On the real line, you have, let's say you have an infinite string, okay? And you have some y value. So you have displacement in y, okay? That will be a vibrating string, right? Infinite string. And f of x will be the initial shape. But then you might also have, at time t equals to 0, certain velocities. Maybe over here the waves are going up, right? Over here the waves are going down. So a moment later you might see that the waves are becoming bigger, right? And then at some point it's going to give you some tension. It might come back to, it will pull back. I don't know what's going to happen. So something like that. So the velocity of the y component of the strings is given by g of x. Okay? So at each point you have different velocity as given initially. Right? And let's try to solve this. This is called the wave equation. Now, you could take this as utt minus c squared uxx equal to 0. And then this is differentiating twice in terms of t. And then this is differentiating twice in terms of x. And in operator notation, you can rewrite this differential equation in this way, right? And because this is a difference of two squares, you might even factor this like and then let's put minus first. Like that. Okay, so a squared minus b squared is a minus b times a plus b. So you can factor this, and this is same as the original one. I'm just rewriting the same equation in different ways. Now, it would be nice if this was merely a differentiation by some variable differentiation by another variable, right? And doing slight changes back and forth, you will see that if you do a change of variable where p is equals to x plus ct and q is equal to x minus ct, so that u is a function of p and q, which in turn is a function of x and y. Right? And then if we do a change of variables from x and y to p and q, maybe the equation might be simpler. Okay. Yeah. Now, if you're like questioning where I got those change of variables, is that you'll see later this turns into rate of change of p and so on and so on. Okay. You'll see that later. Okay. And this. I didn't figure this out right away. I had to like go back and forth and try this and that, and eventually figured out that this is the right one. Okay. All right. So let's try. So u differentiated with respect to x is u differentiated with p, xp, and u differentiate with q, and xq, because x goes through both p and q, right? So this one is this much is this much, right? X goes through q, which is x goes through q, q goes through u. Right? Multiplying these two gives you the rate of change of u when you change x going through q. Okay. Now, what is p differentiated by x? What's p differentiated by x? 1, right? So this is just round p. Okay. What's q differentiated by x? 1 as well. So it's just this. Or now let's try to do t. Okay. In this case, it's again the multivariable chain rule. Okay, what's p differentiated by t? C is a constant. So if you take p and differentiate by t, what do you get? Just c. So it'll be c round p u. How about q differentiated by t?
Negative c.
Negative c. Round q u. Which is same as, it'd be like c times round p minus round q of u. Okay, now let's try second derivative of u with respect to x. And that's, well, differentiation by x is same as differentiate by p plus differentiation by q, right? So it's like this. Now, if these had some p and q in front, then when you differentiate, you have to use product rule, and it becomes really complicated. But because these are constant coefficients, you can just calculate as if they are like polynomials. You can just multiply them like polynomials if they're constants. If it's not a constant, then you really have to work out the product rule. So it's much more complicated. You will have to do that on the homework. But here, we'll just take a shortcut. Instead of using the multivariable chain rule, I'll just multiply them. And this is just binomial identity, right? It's like a plus b squared equals to a squared plus 2ab plus b squared, right? So just like that, this would be partial p squared plus 2 partial p partial q plus partial q squared. If you don't believe me, you can just work this out like the previous examples that we did, and you'll see that the answer is the same. Okay? Only because these are constant coefficients. There's no function of p and q in front. In the same way, this would be c times round p minus round q, and then another c times round p plus minus round q of u. So the c squared times, again, this times this, you expand like a polynomial, it's going to be round p squared minus 2 round p round q plus round q squared. Okay, now that we have the second derivative in terms of x and second derivative with respect to, sorry, why did I flip y? This should be t. Sorry. Okay. So I have the second derivative with respect to t here, right? So I can just replace these. And what it does is you've done a change of variable to a partial differential equation. Now the partial differential equation is written in terms of p and q. U is, instead of being a function of x and t, now it will be a function of p and q. Is that okay? Yeah. So what you have is this UTT means differentiating twice in t, which is exactly the same as that one, which means I can replace this UTT by what I have here. So I have c squared round p squared minus round p round q plus round q squared of u plus, and then uxx means you're differentiating u twice by x, which is exactly the same as this thing, which means I can replace that by this. So let's plug that in. That's actually minus c squared round p squared minus 2 round p round q plus round q squared u equals to 0. Now, do you see a lot of things canceling? Which ones cancel?
There's a copy mistake.
Oh, yes. This should be a plus, right?
Yeah.
Okay, good. All right. So which ones cancel? When this is applied to that, that's a UPP, right? C squared UPP and minus C squared UPP. So that's canceled. Okay?
So everything but 4 dp.
Yes, exactly. So these cancel, and because they both have negative 2 in front, these double, and you end up with negative 4c squared partial p partial q of u equals to 0. So under this change of variables, what we managed to do was to prove that this turns into this. All good? Yes?
On the first column, we brought
Yeah.
dt squared negative c squared dx squared u
Huh?
equals 0. And
This one, yes.
Why does that turn into dy on?
Oh,
plus
sorry.
dy?
That's a mistake. Thank you. All right. Keep confused. Okay. Sorry that. Hopefully that wasn't too confusing. Okay. Now, this is just a constant multiple, so you can just divide this by negative 4c squared. And here's the result. We did all this work to show that this is the same thing as round p round q of u equals to 0. Okay. I claim that this is a lot easier than solving this one. It's a lot easier. Why? Because now I can just integrate both sides. But you have to be careful because you're not doing regular integration, you're doing partial integration. Okay? You're integrating with respect to one variable, pretending that the other one is a constant. So if I take this one, so remember our p is x plus ct, y is x minus, q is x minus ct. Now let's actually solve this. Okay. So let's solve this one. So I'm just going to integrate both sides by p. Now what happens on the left side? If you differentiate by p but integrate by p again, what happens?
Cancel.
They cancel, right? So you get round of q equals to u. If you integrate 0, what do you get? Huh? What's the antiderivative of 0? Constant c, right?
Yeah.
However, we're doing partial integration. In that case, constants could be
CQ.
CQ. It could be a function of q. You remember that? When you solve exact equations in differential equations, the antiderivative could be a function of the other variable. So since this is a partial integration, you're considering q as a constant. So functions of q will be considered as a constant. Now if you don't understand what I just said, just take this equation and differentiate both sides with respect to p. What do you get on the right side if you differentiate yq by p?
0.
0, because q is considered as a constant. That's why if you integrate, you get y of q. Let's see, let's not say y. Let's say g of q, okay? Some function g, right? Is that okay? Right. Now, let's integrate both sides by what? dq. They're going to cancel, so now you found out what upq is, right? Or let's just say u. U is recovered on the left side. However, if you integrate a function of q, I don't know what that is, but it's still a function of q, don't you think? Right? So let's just say the antiderivative of g is capital G. This is what you're going to get. Plus what? Plus? Huh? But instead of c, it's? Yeah, it's a function of p. Some function of p. Right? Now, I guess I made some mistakes here because I already used f and g for something else here. So, well, hopefully this g and that g is different, okay? Yeah. Now we're going to put the initial conditions. But this is what we just solved. U is equal to some function. Let's just call this, instead of g, let's just call this as phi. Okay? Some function, oh no, I want to call this one as phi. Okay? So it's some function of p plus some psi of q. Okay, you know, as math becomes harder, you end up using a lot of Greek letters, so you should try to learn to read Greek letters. This is called phi, or phi. This one's called psi. Okay? So make sure you can read them. Phi and psi. Okay? Okay. And which means that u of xy is now phi of, what's p? P is x plus ct, right? Plus psi of x minus ct. Okay? Not xy. xt. Keep using y. So uxt will be phi x plus ct plus psi x minus ct. Is that okay? So that's the general form, but we still haven't used these two conditions. See? We only worked with this one, and we just integrate, we did change the variables and we integrated to get that solution, right? Now we have to throw in the initial conditions. So let's see what happens. If I plug in t equals to 0 for both sides, here's what you get. You get u of x comma 0 equals to phi of x plus c times 0 is nothing, and psi x minus c times 0. I'm plugging 0 into t, so it will just be x. And that has to equal to f of x. Okay? Now, I have to differentiate by t and then plug in 0. So let's try to differentiate this by t. What is ut xt? Well, that requires chain rule, right? So we were thinking of x as a constant, so it's like this. Can you differentiate sine of, let's just say x is, say, 3, okay, and ct. Can you differentiate this by t? What happens? Cosine 3 plus ct times c. Yeah. It's just like that. So if you differentiate by t, x is a constant, so you just bring this outside and differentiate by t. So it'll be phi prime. You differentiate the outside function multiplied by the derivative of the inside function, which is c. Okay. Then plus differentiate the outside function x minus ct times what? Negative c. Okay. And that's going to equal to, oh, not yet. Now we plug in 0. So ut0, x0, is phi prime, or v c times phi prime of x minus c times psi prime of x. Okay, I just brought this negative c in front, plugged in t equals to 0. And that should equal to what? This should be? G of x. Okay. So we're pretty close, because now, see, when I wrote this general solution, phi and psi is some functions that we don't know. Okay, could be anything. And for any phi and psi that can be differentiable, anything that can be differentiated twice, you can plug it into this equation and you'll see that it does work. Okay, yeah. That's what we found out. Okay. However, if you provide the initial conditions like these two, then what happens? Then you can actually figure out what phi and psi are. Okay? So how do we do that? Well, just integrate this from, let's see, right. So what you do is you divide this by c, so you get phi prime of x minus psi prime of x equals to 1 over c g of x. And then you integrate both sides. I have to be careful here. It should be integrate from psi. Let's see, psi tau 0 to I'll just have to integrate this. We're running out of numbers here. I'll put psi, another Greek letter. This is psi. Forgot how.
Is it epsilon?
No, I don't like epsilon.
What about like gamma or something?
Huh?
Gamma?
You want gamma?
Looks. It's kind of like a Y.
Okay, let's use tau. This is tau. Tau minus psi prime of tau d tau from 0 to 0. I'm comfortable with this 0 at the end, but let's just say that this is negative infinity. Okay? With the condition that all of these functions will be 0 at negative infinity. Right? So you don't want an infinite string to have some non-zero value at infinity. We want everything to be 0 at the end. Okay? So we're going to assume that. Okay, and then you integrate, you differentiate and integrate, which will give you phi of t tau. But then you plug in this minus this, but phi of negative infinity is 0, so the left side will be just phi of x. Same thing here. Psi of x will be 1 over c negative infinity to x g of tau d tau. Okay. All right, so that's good. Why is it good? Well, because now I can easily solve this. So look what we found. So after showing that generally the wave equation has this solution, I have two equations for phi and psi. I have this one and this one. Right? And now we can just add them together and also subtract them to find the solution. So let's see. Psi of, I'll just copy that over here. Phi of x plus psi of x is f of x. And then phi of x minus psi of x is integral of negative infinity to x of g tau d tau. How do we find out phi of x? Easy question. How do you find phi of x in terms of f and g?
Yes.
Huh?
Add them together.
Add them together. Okay. You add, and the result is that you get 2 phi of x equals to f of x plus 1 over c integral from negative infinity to x g of tau d tau. And then we can divide by 2. Okay. How do we solve for psi? Subtract. So instead, if we subtract, then these two cancel and this doubles, and you have 2 psi of x equals to f of x over 2, right? Plus, actually, after dividing by 2, you're going to get this one and 1 over 2c. Oh, because you subtracted now, it's going to be minus, right? And then negative infinity to x of g tau theta. Okay. Now, since we figured out what phi of x and psi of x is, now let's replace x by x plus ct and x minus ct, so I can recover what u of xt is. Okay? So it's a humongous formula. I'm going to start here. U xt is equal to phi of x plus ct. So all these x's, here's an x, here's an x, they both have to be replaced by x plus ct. So I have f of x plus ct over 2 plus 1 over 2c, integral from negative infinity to x, g of tau d tau, x plus ct. And then plus, so this horribly looking thing is phi of x plus ct, okay? All right, so let's see if you're following me. What do I write for psi of x minus ct? What do I write here? Uh-oh, you guys are not following me. There's just calculation here. See, this much is phi x plus ct, okay? Yeah. So I just have to now write this one. What's that? I have psi of x.
Of x minus t over 2
minus
over 2c. Same thing, really. X minus t.
Okay. Now, I'm going to simplify this yet again by using the following fact that if you have integral of a to b minus integral from a to c, this is integral from c to b. Right? Is it right? Because if you have f here, that's like fb minus fa plus minus fc minus fa. So they cancel, and then it's fb minus fc, which is this one, right? Okay. So if I use that to put these two things together, here's what we get. It's instead of from negative infinity to this, it's this to this, and these two can add up. So my final solution is uxt is equal to f of x plus ct plus f of x minus ct over 2 plus 1 over 2c integral from x minus ct to x plus ct. And then g of tau. That's it. Okay, so that's the general solution. Solving this, it satisfies the differential equation, it satisfies the two initial conditions, and because we know that the solution is unique, this is the only solution. By the way, I said that we really don't solve PDEs, we just guess them, but this is more like an honest solution. We actually honestly solved it. The other ones will feel more like guessing. But this is an honest solution, I would say. And this has a name. This is called that's called the D'Alembert solution of the wave equation. And just to give you an idea of what that does, so here's an example. suppose you have UTT equals to 4 UXX and UX0 as e of negative x squared, and then UTX0 as 0. Just to see what this formula is telling us, let's just try to apply it to this specific case. Okay. So what's the value of c? 2, or negative 2, but it's you get the same thing, so we will just say c is 2. So c squared is 4, so c is 2. And because g is 0, this interval is not going to give you anything, so that's gone. The only thing will be this one, right? So the solution, according to D'Alenberg's formula, would simply be uxt equals to e to the negative x minus 2t, actually plus 2t squared, plus e to the negative x minus 2t squared over 2. Now what does that mean? Well, here's an infinite string, and you have a wave that looks like this. Okay, so this is what's known as the normal curve. Okay? Actually, you have to divide by something to get the normal distribution that you use in statistics. Okay, I think this is divide by 2 and then divided by square root of 2 pi. I think 1 over the square root of 2 pi. Then the integral gives you 1 under the curve and all that. Well, that's not important. If you draw the curve, this will be the shape. Okay, and then initially, the initial velocity is 0, so it's like that. Okay. Now, think about what's going to happen with this string. It's going to try to go back, right? Yeah. It will try to go back to the equilibrium, but then as this thing goes down, right? It splits into curves that move in 2 directions. So when t is equal to 1, what does this mean? This means that this curve is moved left by 2, right? I mean, if t is 1, what is that? E to the negative x plus 2 squared. What's that? What's the relationship between these two? This moved 2 steps to the left, right? Yeah. What about this one? It moved 2 steps to the right. So what happens is that this thing splits, and then at time t equals to 1, you end up with something like that. Okay? And the peak would be following this line, which is given by x equals to 2t. Okay? Or plus minus 2t. This is x equals to 2t, and this is x equals to negative 2t. And these two lines are called the characteristic lines. They split, and then they go to infinity. That's what happens.